This video will go over section 4.2 on Lewis structures, 4.2a, part A of section 4.2. So Lewis structures are electron dots structures for molecules. They show the location of all valence electrons. So up to now we've learned how to do the electron dot structure for atoms, but now we can do it for whole molecules. Because the molecular formula shows only the number and identity of all the atoms in a compound. And for example, a molecular formula like CH4 or NH3 or H2O, you see the type of atom that are in the molecule and how many of them, but you don't know more than that. It doesn't tell you which atoms are bonded together and more information about the molecule. So Lewis structure shows which atoms are bonded and how valence electrons are distributed. So Lewis structures are given in this middle column here. For example, for CH4, you can see that each hydrogen is bonded to carbon. In NH3 for ammonia, each hydrogen is bonded to nitrogen. And in water, the two hydrogens are bonded to oxygen. So it gives you more information and it gives you the location of the valence electrons. So we will learn to draw Lewis structures, and the general rules to follow for drawing Lewis structures are that you want to draw only the valence electrons. The core electrons are omitted. You want to give every main group element an octet of electron. So there are exceptions here. Remember how hydrogen only wants a duet, but otherwise all the other atoms want octet of electrons, which means 8 valence electrons around them. So hydrogen will only want 2 electrons around it. So how to draw a Lewis structure? The first step is to position the atom with the more metallic atom in the center. The more metallic atom is always the first atom in the formula. So that's typically the one you will want to put in the center of your structure. And another thing to consider is that hydrogen and halogens will always be on the periphery of the structure because they can only form one bond. So for example, for CH4, you would put the carbon. Carbon is first in the formula, so you would put it in the center. And you would surround the 4 sides of carbon with hydrogens. Let's consider that there's no more than 4 sides around the central atom. And so, for example, you would not position the carbon like that, surrounded by 3 hydrogens, and then have another hydrogen bonded to one of the hydrogen. This is not possible because hydrogen cannot form 2 bonds. So that would be something you don't want to do. So you want to follow the common bonding patterns to arrange the atoms. The common bonding patterns were seen in section 4.1. And so, for example, for CH5N, carbon tends to make 4 bonds. So you want to surround it with 4 atoms. And nitrogen tends to make 3 bonds. So you want to surround it with no more than 3 atoms. And so that's why you would place here, in the case of CH5N, you would place carbon and nitrogen in the center and give 1 more hydrogen to the carbon than to the nitrogen. You don't want to do the reverse and give more hydrogens to the nitrogen. That would not make sense because nitrogen can only make 3 bonds. Carbon, on the contrary, can make 4 bonds, so you can give it 4 electrons, 4 atoms around it. So the second step is to count the number of valence electrons that are available. And so remember that for main group elements, the number of valence electrons is equal to the group number from the periodic table. And then you take the sum of all the electrons available, and that will be your total. That will give you the total number of valence electrons that you will need to distribute in your Lewis structure. So for example, for CH3Cl, so you have one carbon. Carbon being in group 4A brings 4 electrons. So that one carbon will bring 4 electrons. 3 hydrogens, each hydrogen bring 1 electron. So 3 hydrogen times 1 electron, it's 3 electrons from the hydrogens. And then chlorine is in group 7A, so brings 7 valence electrons. And there is only one, so plus 7 from chlorine. 7 plus 3 plus 4, that's 14 valence electrons in total for CH3Cl. And so you want to keep that number in mind and check that at the end you have this correct number of valence electrons. So the third step is to distribute the electrons around the atoms. And so first you want to place one bond, which means 2 electrons, and it's drawn as one line between every 2 atoms. So for main group elements, you want to give no more than 8 electrons around them. So pay attention to not exceed that, or make sure you have that number. Hydrogen, remember to not give more than 2 electrons to hydrogen. It only wants a duet. And when it has done a single bond, hydrogen is all set. Once you have done your single bonds, then you use all the remaining electrons to fill the octets with lone pairs, starting from the atoms on the periphery. So that means you do not start with the central atom, you start with the atoms on the periphery around it. And then you count the number of electrons left as you go to see what you will need to do next. So for example, if we do CH3Cl, so the arrangement would make carbon the central atom, surrounded by the 3 hydrogens and the chlorine. We saw earlier that there is 14 valence electrons available. So you would do first the single bonds from carbon to the hydrogens and to the chlorine. So that's 4 bonds, and they have 2 electrons each. So that's 8 electrons from those bonds. So 14 minus 8, there is still 6 electrons to distribute. And so you would give the lone pairs to chlorine, because hydrogen is already satisfied with 1 single bond. So you don't need to put lone pairs on hydrogen, and you would never do lone pairs on hydrogen. Hydrogen is always bonded with a single bond, and that's it. So chlorine, on the other hand, needs 8 valence electrons around it. When it has only a single bond, it needs 6 more electrons. And so you would provide them with lone pairs on 3 sides. So 3 lone pairs times 2 electrons, that's 6 electrons. And that use all the 14 electrons that were available. So you have used all the electrons that were available. And if you look at it again, you see that you have 14 electrons in total. 8 around carbon, plus 6 more around the chlorine. So 8 plus 6 is 14. So you know this structure is correct. So if all valence electrons are used, and if an atom still needs more electrons, if it doesn't have an octet, then you would proceed to step 4. And step 4 is to use multiple bonds to fill octets when needed. But before we see examples of that, let's practice Lewis structures where there is no multiple bonds. So we will practice first with PCl3. So try to do this on your own before you watch the answer. So draw the Lewis structure for PCl3, phosphorus trichloride, which is used commercially to prepare insecticides and as a flame retardant. So we said that you want to place the first atom in the formula in the center because it's usually the most metallic. And if you look at phosphorus and chlorine, phosphorus is to the left of chlorine, so it's more metallic. So you would place P in the center and surrounded by the 3 chlorines. Next, you want to calculate the total number of valence electrons. So looking at P in the periodic table, it's in group 5A. So P provides 5 electrons. There is only one P. And chlorine in group 7A has 7 valence electrons. There is 3 chlorine. So 3 chlorine times 7 electrons each. That's going to be 21 electrons from the 3 chlorines. Plus the 5 from the phosphorus, that's 26 electrons total for the structure PCl3. So the next step is to attach each bonded atoms to the central atom with a pair of electrons represented by a bond line. So a bond line means 2 electrons. So we make 3 bonds here, and then you want to remove those 3 bonds or 6 electrons, because 3 bonds times 2 electrons each, that's 6 electrons that you want to remove from the total. So 26 minus 6 bonding electrons, it's 20 electrons that still need to be distributed. So the next step is to place the remaining electrons using lone pairs to complete octets of outside atoms first. So the outside atoms here are the chlorine, and you want to give them an octet. Right now they only have 2 electrons around them, so you need to add 6 electrons for each chlorine to get 8 electrons around each chlorine. So it would look like this when you have placed 3 lone pairs on each chlorine. So 3 lone pairs times, so there is 3 lone pairs times 2 electrons each, that's 6 electrons per chlorine. You have 3 chlorines, so 3 times 6 is 18 electrons that we just placed there. So out of 20, we still have 2 electrons. And so the chlorines have their octet, but phosphorus doesn't have an octet. So the 2 electrons remaining will go to phosphorus. And this way, phosphorus will have 6 plus 2, 8 electrons around them. So we will use those 2 electrons on phosphorus. And so 18 plus 2, that's 20 electrons in total that have been distributed. And so now if we count, do we have 26 valence electrons in total? So, 6 on one chlorine plus 6 on another chlorine, that's 12, plus 6 on another, on the third chlorine, that's 3 times 6, 18. Plus the 6 from the single bonds, that's 24, plus 2 on the phosphorus, that's 26. So we have 26 valence electrons in total, and each atom has an octet. So you want to check those 2 things, that you have the correct number of total valence electrons, and that each atom has an octet, or a duet if it's hydrogen. So this structure is correct. Let's practice again with Cl2O. So here the central atom is not necessarily chlorine, even though chlorine comes first in the formula. Between chlorine and oxygen, it's hard to tell which one is more metallic. But one thing about molecules is that they always tend to be symmetrical. So here, because you have 2 chlorine, 1 oxygen, you want to put the oxygen in the center and surround it with the chlorine. Another argument for this arrangement is that the chlorines are halogens, and halogens can only form single bonds because they have already 7 valence electrons. So they need 1 more, and by sharing a single bond, they will get that extra electron to get their octet. So you would put oxygen in the center, surrounded by the chlorine. Next, you want to calculate the total number of valence electrons. So we have 2 chlorines. Chlorines are in group 7A, so they have 7 valence electrons. So 2 times 7 electrons from the chlorines, plus 1 oxygen. Oxygen being in group 6A brings 6 valence electrons. So 14 plus 6, that's going to be 20 electrons. So 20 electrons for Cl2O. So first you will attach the atoms together with single bonds. So you put a line between Cl and O and Cl. And that is using 4 electrons because 2 bonds and each bond has 2 electrons. So that's 4 electrons there. So you subtract that from your total, 20 electrons minus 4 bonding electrons. That's 16 electrons remaining. The last step is to place the remaining electrons using lone pairs to complete octets of outside atoms first. So that means you want to complete the octet of the chlorine before you do the central atom. So you would place, so chlorines right now, they have a single bond, which means 2 electrons. They need 8. So you need to give them 3 lone pairs, which means 6 electrons, plus the 2 from the single bond that will make octet for the chlorines. When you do that, you are using 6 plus 6, 12. So 16 minus 12, you still have 4 electrons. Those 4 electrons now will go to oxygen because the chlorines have their octet, they don't need anymore. And the oxygen has only 4 electrons around it, two bonds of 2 electrons each. So you need to give it 4 more electrons. And so we have those 4 more electrons available to give a lone pair to oxygen. And we give it 2 lone pairs that use the 4 electrons that were remaining. And so now you want to check that, so each atom has an octet. So the chlorines have 6 from the lone pairs plus 2 from the bond, it's an octet, each of them. Oxygen has 4 electrons from the bonds plus 4 from the lone pairs, that's an octet. And now you want to count the total number of valence electrons and make sure you have 20. So 6 from chlorine plus 6 from the other chlorine, that's 12. 4 plus 4 from the bonds, that's 12 plus 4, 16. And then 16 plus 4 from the lone pairs on oxygen, that's 20. And so we have our 20 valence electrons in total. And so this plus the fact that all atoms have their octet makes you sure that you have the correct Lewis structure.